Hi everyone, sorry for the wobble right at the beginning. I first want to formally write down a couple of things that we've been saying, and then I want to use the first derivative test in particular to work through another problem once we know the kind of official definition of what it is. Okay, so I hope this first one is easy. Sorry, my printer kind of ate this thing. Derivatives and graphs. Okay, so we want to remember f prime tells us about the slopes of the tangents to the function, which means if f prime is greater than 0, the slopes are positive and the function is increasing. And if f prime is less than 0, the slopes are negative and the function is decreasing. Okay, so the first derivative test is entirely based on that. So what we want to say is if we have a function that's continuous at a critical number, we wouldn't call it a number unless it was continuous anyways. So let's just say if we have a function and we are looking at a critical number, an x value where the derivative is either 0 or undefined, and we know that the derivative switches from positive to negative. That means it switches from increasing to decreasing. The function switches from increasing to decreasing. And that means that at that corner or flat spot, whichever it is, the function has a local max. And if the opposite is happening, the function's derivative is negative and then positive, that means the function is decreasing and then increasing, and that's a local minimum. And in this way, if we can find the critical values of a function, we can then investigate what's happening nearby to decide if they're local maximums, local minimums, or neither. So it would be neither if we didn't switch. If it went positive and then there was either a flat spot or a corner and then it stayed positive, or negative and then stayed negative, that would not be a max or a min. It would be maybe an inflection point, maybe. Okay, so we are first supposed to, in this problem, we're going to do a first derivative test. So first we're supposed to find the critical values and then we'll do the test to see what they are. So I gave us kind of a messy one. G prime is going to require a quotient rule. So I have the bottom, x squared minus 2x plus 1, multiplied by the derivative of the top, which is a 2x plus 1, minus the top, x squared plus x minus 6, multiplied by the derivative of the bottom, which is a 2x minus 2. And that's going to be divided by an x squared minus 2x plus 1 squared. Okay, so kind of a mess. Our big goal here is we're finding critical values, so we want to know when g prime is equal to 0 or when g prime does not exist. But I actually know for the second part I'm going to be making a sign chart, so I'm just going to work on simplifying the derivative before I focus just on answering that question. So right now I can't do any canceling because of the subtraction on the top, so I'm going to multiply all this out and then try to factor and cancel. So this 2x plus 1, I'm going to go ahead and distribute it through. You could think about this opposite as well. Take this whole quadratic and distribute it through, whichever way. So when I multiply the 2x plus 1 by an x squared, I get a 2x cubed plus 2x, oh, not 2, 1 x squared. And then when I multiply the whole thing by negative 2x, I get a negative 4x squared minus 2x. And when I multiply it by 1, I get a 2x plus 1. And then over here, ooh, you know what I'm going to do? Since I have to distribute a 2x minus 2 through and I eventually have to distribute the minus sign through, I'm going to go ahead and just distribute the minus sign through. It only goes through one though, not both. If you multiply by a negative and a negative, then you really just multiplied by a positive. So pick either one. I'm going to do this one and distribute that minus sign through. So that becomes minus plus. You could also just do the distributing and then distribute the minus through in the next step if you prefer. Okay, so x squared multiplied by all of this. This is a negative 2x cubed plus 2x squared. X multiplied by that is a negative 2x squared plus 2x. And then negative 6 multiplied by all of that is a 12x minus 12. Almost ran out of room. Okay, and then the bottom, right now the bottom is really fine, but I can see that x squared minus 2x plus 1 factors really nicely, so I'm just going to go ahead and do that. X squared minus 2x plus 1 factors into an x minus 1 squared, and then if you're squaring all of that, you actually end up with 4 of them down. Okay, so let's clean up the top a little and see if it factors. I can see my 2x cubes going away completely, which is nice. Quadratics are much easier for me to factor than cubics. Over here, I see some 2x squareds dropping out. Is there anything else I can get over here? I see some 2x's dropping out. Okay, I don't know that the rest of these are just going to go away. So let's just see what we have. G prime is equal to, okay, so I see a negative 3x squared. And then I see, dealt with that, 1, okay, 2x, 12x. So I see 14x, and I see negative 11 all over x minus 1 to the 4th. And then I'm going to try and factor. That looks terrible, but let's try. Otherwise, what we're going to end up doing when we set this equal to 0 is a quadratic formula. So if I factor out the negative 3x squared minus 14x plus 11, you don't have to do that, but I always prefer to factor trinomials when there's the minus sign not in the front. Actually, I think that works out kind of nicely because the 3 and 11 add up to 14. So if we just divvy them up, 3x and x, and then we'll want the 11 and 1 to go that way. So we get 3x and 11x, which adds up to 14. But we really want negative 14. So we'll make it negative 11 and negative 1. Which is actually kind of fantastic because we can cancel out an x minus 1. So I get g prime of x equals, I'm just going to put the negative out in front, or you could distribute it back in, or you can leave the parentheses, whatever you like. X minus 1 cubed. Okay, so there's my derivative. Simplified version of it. So back to what this question was really asking. This question was asking for critical numbers. So if I want to know when g prime of x equals 0, the fraction is only going to equal 0 if the top equals 0, which means that x has to be 11/3. I also want to know when g prime does not exist. And g prime doesn't exist when x equals 1. That makes the denominator 0, which is a bad sign, but we have to be really careful in this one. I don't know if I stressed this a whole bunch when I gave you the definition of critical numbers, but it does say in there a critical value or number, it's the same thing, sorry if I switch back and forth, is an x value in the domain of the function for which the derivative is 0 or undefined. So if you get a potential critical value, if you figure out that the derivative is undefined in particular is the tricky one, you want to go back and make sure that the function isn't also undefined, because if the function isn't undefined, then there's a hole or an asymptote or something like that, and there's no way that there's going to be a maximum or a minimum at an asymptote or a hole in the graph, so that would mean it doesn't count as a critical value. And that's actually exactly what's going on in this function. If you plug the 1 back in here, you get undefined as well. So while it is interesting when we're making the sign chart to note that the derivative doesn't exist, so let's see, g of 1 does not exist, which means it's not a critical value. So the only critical value is 11/3. So I think I kind of interrupted my own self. It is interesting when you're making the sign chart to note when the derivative is undefined, but that doesn't count as a critical value. There's not going to be a max or min there. So when I come down here to make my sign chart, I am going to mark off, I don't know why that just got a y-axis, pretend that's not there. Or we can just say that it's x equals 0, that's fine. I'm going to mark off x equals 11/3, which is what, 3, 6, 9 and 2/3, 3 and 2/3. So we'll go 1, 2, 3. So right around here is 11/3, and the derivative is 0 at that point. I'm also going to mark off x equals 1. but I'm going to remember that no matter what's going on my sign chart, there's no way that I would ever call that a max or a min. So the derivative might change signs there, but I'm not going to find a max or a min there. So really the key reason that I put that here, all I care about is what's happening on either side of 11/3. But if you forget to remind yourself that the derivative might change signs back here, when you go to check on the left-hand side, you might check 0, and that's actually not helpful because whatever's happening at 0, it could switch to something else over here. So that's the biggest reason we want this. So we want to check something in between 1 and 11/3 and something bigger than 11/3. Okay, so I'm going to go ahead and just check 2. 3 would work as well. Integers are nice just because they're easy to plug in. And I have this really nice simplified version of my derivative back here. So when I plug a 2 in, there's a negative out in front. I get 6 minus 11, which is a negative number. And then on the bottom, I get 2 minus 1, which is 1 cubed, which is positive. So a negative times a negative divided by a positive, that's going to be positive, which means my function is increasing. At 11/3, I know I have some sort of flat spot. And then if I go on this side, so 4 would work, I'm going to go out to 5, give myself a little room to write. If I plug in 5, I have the negative out in front, and then I get 15 minus 11, which is positive. You can write down 4 if you want. And then 5 minus 1 is 4, cubed is positive for sure. So that's going to end up being negative, which means my function then decreases. So what this is telling me is that at the critical value, there is a local max. So local max at x equals 11, I'm sort of sneaking off the bottom, thirds. Okay, so there's my first derivative test. We really didn't complete the sign chart. We don't need to for the first derivative test, but since it says to make a full sign chart, I'm going to go ahead and just plug in 0 to finish this off. So at x equals 0, I have the negative out in front, I get a negative 11 in the top, and I get negative 1 cubed in the bottom. So negative times a negative divided by a negative is negative. So this function decreases and then increases and then decreases. But once again, I want you to be really clear that this is not a local minimum because the function is undefined here. So I think what we're really seeing is that there's a, let me think, the function is decreasing and then the function is increasing. Cubed. I don't think it should switch. Did I mix something up? Negative 1 cubed negative. No, I think it's okay, but somehow, I don't know quite what it's looking. Maybe it's doing that. No, it's supposed to increase. Somehow this is an asymptote, so there's not going to be a max or a min there. It's not possible. Okay, so I think that's it for that one. Thanks for watching.